Hello and good afternoon, and welcome to Doc Clay's Quick Questions. We are just going live now. Hopefully, I'm just going to give everybody a few minutes to sign up and log in and see how we're doing. I hope you are all enjoying the lovely weather out there. Not a great day to be stuck inside doing a webinar, but I won't keep you long today. Okay, so we are just at coming up to 4 o'clock now, and hopefully you should be able to see. Hopefully you should be able to see the screencast here, and today we're going to be looking at the two practicals associated with the A2 course. This week we're going to look at the electrochemical cell and pH meters and pH acid-base titrations and the titration curves. So we looked a bit at titrations last week, so that sort of leads on nicely with our acid-base titration curves, and also tomorrow's live webinar is all on electrode potentials, so we're going to look at the electrochemical cell in this session and potential relevant questions. So for those of you perhaps who haven't joined our site today, I'll just take you on a quick run around. Hopefully you might be able to see the site. You can come along to Doc Clay's A-Level Chemistry. If you want to join in the chat, if we go to the webinar and we go to today, we're on quick question. So this is viewable to all our users. You'll find we've got the chat. You can find the live stream there. And then at the bottom here, you should be able to find our chat room. Please do drop me a line in the chat room. It would be great to talk to you. Feel free to ask questions as we're going through. You'll also notice that the resources for the session here can be accessed. So check out the OneNote resources and also the questions. We will look through most of those in this session. For those of you who are members of the site, you can also go to the past webinar section and you can pick up today's webinar and the quick question webinar, which is in quick practical questions on the 3rd of May, Ecell and pH. And if you scroll down the screen here, you'll get to there. We've got the live feed. And you'll see we've also got the answers, the questions, and again, the link to the OneNote page and OneNote document. All of this, like I say, is accessible here directly through from drclays-alevelchemistry.com. If you're wanting to follow a link, simply drop to the bottom of the YouTube page, and we're going to get going in just a couple of minutes. Okay, we're going to get going. What's the webinar on today, Joe? Yes, thanks for the question. Today's webinar, we're going to be looking at practicals. We're going to be looking at electrochemical cells and also pH, which are the required practicals, 8 and 9, I think, from the required practicals list. I'm going to give all our members 1 more minute to log in, and then we're going to get going. Obviously, if you want to watch this again after the webinar has finished, feel free, just drop along, check out the webinar section, go to either past webinars here, and you'll find all of the previous webinars for our users online. Just come along, have a look, all the resources there. Feel free to ask any questions. Also, the webinar tomorrow night is all going to be on electrode potentials. Okay, the other thing that I would request, if you're going to ask questions throughout today's webinar, if you can just take yourself, everyone can access this page from the home page. Just go to the quick questions video. That's where we're running today's webinar. So all viewers can see, and if you could ask your questions through the webinar today through the blue chat room here on Doc Clay's practical questions. That way I don't have to keep following just our chat that we got on the side there. All right, that would be much appreciated. Okay, so I think we're ready to go. It's coming up to, we've been online for about 4 or 5 minutes now. Hopefully everybody's had a chance to log on, and like I say, if you've not done so already, do sign up to the site. Make sure that we've got going on. Just a quick question again, please do use the chat. Electrochemical cells, absolutely. That's right, Julianne. Right. So there are 12 required practicals that you need to know about. We're going through these over the coming weeks. Last week, catch up if you missed it, on enthalpy change in volumetric solutions. That was our, as well as titration, that was last week's webinar. This week, we're going to carry on and we're going to look at something really associated with acid-base pH changes, so sort of linked to our titration calculations from last week. And then we're also going to look at the electrochemical cell, and that fits in quite nicely because tomorrow night's webinar, we're going to be looking at electropotentials and the theory of electrochemistry, again with heaps of resources. So feel free to access the OneNote page here. We've got the key points documents, and then we're going to spend 10 minutes just going through some related practical questions for you associated with these two key practicals. All right, so here we go. We've got to know about two practicals. We're going to start off here. I'm just going to move this one out of the way for us. We're going to come across here with measuring pH and doing titration. So if we look at the required practical, we're saying investigate how pH changes with a weak acid reacts with a strong base, and when a strong acid reacts with a weak base. So the key here that they're interested in us being able to do is, can we identify pH as a function of volume of acid or base added? Can we observe what our expected graphs would look like, and also can we then describe how we might measure the pH doing a titration? So there's a couple of things that we need to be aware of. First of all, obviously a strong acid is going to have a low pH. So we'll look at acids reacting with the addition of alkali to start with. Strong acid is going to be a pH of around about somewhere between 0 to 2, and our weak acids here are going to be around about sort of pH, that should be pH, sort of 2, maybe to about 4, our starting values. We've got a pH scale here of 0 to 14. And if we're going to start off with a strong acid with our addition of OH minus, I'm going to draw this on as a blue line. We're going to continue to add OH minus, and then at some point we're going to get a sharp rise in the pH, and this point here where we get a sharp change is what we measure as the end point. Notice we're adding a OH minus to a strong acid, so we're starting at low pH, and we're seeing a change, an increase to a high pH. Okay, so that's what we get if we get a strong acid. Now if we move over to a weak acid, well, we see a slight change. I'm going to add our change here in green, and we would end up here with a curve where the start is characteristic start, and we get an initial curve which looks like this, and then we get a change, and we follow then the same pattern as we had before. So my green line here is indicating that of a weak acid along both instances here with a strong alkali. So there we got the, like I say, what would happen if we were adding a strong acid to, adding a strong base to either a strong acid or a strong base to a weak acid. Now, the key thing in both of these cases, again, I'm just going to move my electrochemical out of the way here, is that to measure the endpoint, it's the sharp rise, and we need an indicator that changes color over the endpoint range. Now, there's two that you have to know about. Or the other indication is you might be given some data and you need to be able to indicate exactly which pH would be a sensible one to go about. Two that we need to know about, so that you are aware, is that, let's do these down here, is we must be able to recall phenolphthalein. Oh, I was going to do that in red, but it's come out as green. Sorry about that. So phenolphthalein and methyl orange. These are our two indicators. The key here is that our phenolphthalein changes color from 8.3 to 10. And this is going to be pink in alkaline conditions, and it's colorless in acidic condition. Well, I say acidic, but less than 8.3. Methyl orange, oh, sorry, I'll put those in the wrong bit there. That's our phenolphthalein. While our methyl orange, apologies for that, is going to be 3.1, is a lower pH to 4.4, and this is yellow in acidic, or at least pH is above 4.4, and it's red below 3.1. What that means is for our strong acid and our strong base, we could use either universal indicator because the endpoint occurs in those range. Whereas with a weak acid, we couldn't use methyl orange. We'd have to use phenolphthalein because the color change occurs 3.1 to 4.4. And if we look here at our graph, I'll just show it in red, the most likely thing is that this is not seeing a sharp change around 3.1 to 4.4. So methyl orange would be no good. Now, if we are going to be doing a addition of an strong base to a strong acid, or a weak acid to a strong base, then we're going to see the exact opposite sort of graph. So if we had pH with volume of H plus added, and we started with a strong base, so we're going to be up here. If we had a strong acid, we would get the exact opposite. While if we had a strong alkali with a weak acid, we would see again a similar curve, which would then tail off in the opposite way that we've just seen before. Again, methyl orange is only going to be any use for the addition of the strong acid with this strong base, while phenolphthalein could be used for either addition. The final thing to note here about, let's just move this final one out of the way. Let's get this so that we're not being taken over. We've got our addition of the weak alkali version to this system. So if we had a weak alkali and we had a strong, and we're adding a volume of H plus added, let's go for this time. Our weak alkali and strong acid will go like this, where we've got a weak alkali with a strong acid. But the key here is if we have a weak alkali with a with a weak acid, what we'd end up with is we'd end up with a curve where it sort of did this. And the thing about the addition of the weak acid and weak alkali is there's no sharp endpoint. And therefore, in order to do this pH calibration, we would need to use a pH meter, because we simply can't use a color indicator. Okay, so they're the key things really about our practical for acid base. The next thing then finally is we're going to look at our electrochemical cells. So we're going to come down here, we're going to look at reactions with electrochemical cells, and then we're going to have a look at some example questions. Will take us to about 4:30 there, and we'll be done for the session. So here we got an electrochemical cell. Key things about measuring the electrode potential of a cell is these must be done under standard conditions. So in order to get true values, we need to use standard conditions, which for all of these purposes is going to be 1 atmosphere of pressure. We're going to have to use 298 Kelvin or 25 degrees Celsius as room temperature, and we're going to use 1 mole per decimeter cube. Now just be aware of that, because if we're using, let's say, H2SO4, then to get 1 mole of hydrogen ions, it's equivalent to 0.5 mole Dm-3 of H2SO4. So there is just something to be aware of there. 1 mole per Dm-3 of hydrogen ions is equivalent to half a mole Dm-3 of H2SO4. Okay, so that's the first thing we have to be aware of when we've got standard conditions. The other thing is, when you're drawing these things, is you must have something, some sort of electrode. So the electrode must be solid and it must conduct electricity. So if you're doing 2 solutions, then you may need to use either carbon or platinum, because those 2 things are inert and then won't affect half cell equations, and we'll be looking at this in more detail tomorrow night. The other thing is that in order for a reaction to occur, we require a salt bridge, and that must be dipped into the solutions, because if it's not dipped into the solutions, then no current will flow and no potential difference will be measured. So that must be dipped into solutions. And the final thing then is you require a high resistance voltmeter connected between the electrodes, and it's a high resistance voltmeter because without it being high resistance, what happens is that a current would flow and that would change the electrode potentials. So that is why we require a high resistance voltmeter connecting them together. Otherwise, that requires in the question is to be able to produce a picture not dissimilar to this. So what we're going to do in the next sort of 10 minutes, 5-10 minutes, is we're going to just have a quick look at some practice examples. There's heaps more examples on the website there. If you want to check them out, just pop on to the past webinars page. You'll find, or sorry, in the live webinars page here in quick questions, you'll find them here. And if after the webinar you want to double check through lots of the answers, then you can just go to the past webinar page. So we're going to have a look at some of these practice questions that we've got here. You'll find them, Ecell and pH practical questions. If you're wanting to check out the answers for these afterwards, you need to log into the quick question webinar, the past webinar section of the site, which is here. Go to quick question webinar, which is quick practical questions 3rd May, Ecell and pH, and you'll find the answers just there. Okay, let's go and have a look then at some questions. Okay, Like I say, we're going to deal predominantly with practical questions here, and anything not practical we will save for tomorrow night for the electropotentials webinar that we got at 8:30 p.m. An experiment was carried out to measure the EMF of this cell. So here we've got aluminium with hydrogen. The aluminium used as the electrode is rubbed with sandpaper prior to use, suggests the reason for this. Okay, so why do we need to clean the surface layer? And the answer to that is on the outside of any metal, you're going to get an oxide layer, and that needs to be removed, because otherwise, if you think about it, a metal oxide is going to be an ionic substance, and those aren't going to conduct electricity. Okay, draw a labeled diagram of a suitable apparatus for the right-hand electrode in this cell. You do not need to include the salt bridge or the external circuit. Okay, so here we are. We've got platinum. This is actually the standard hydrogen electrode. We'll talk about this in more detail, but the key is that you've got the platinum electrode. You're going to have a solution, like we said, which is going to have one mole Dm-3 of H plus ions, or you could say half a mole Dm-3 of H2SO4, and then as well into there you're going to have hydrogen H2 bubbled at 1 atmosphere pressure. Okay, so they're the key points. Like it says, it doesn't need the rest of the external circuit, and that is called the standard hydrogen electrode, or SHE for short. Okay, a simple salt bridge can be prepared by dipping a piece of filter paper into a potassium carbonate solution. Explain why such a salt bridge would not be suitable for use in this reaction. So that really is talking about electrode potentials, and it's talking about reactions. But if you're thinking about, you've got a carbonate solution, you're talking about an acid, so there's going to be a reaction between a carbonate and the acid. So just be aware of practical issues like acid-base reactions occurring in a cell reaction. Sorry, that should say reaction between the carbonate and the acid that we've got in our sample. Okay, number 3 then. Okay, so biocide is chemical that kills bacteria. A biocide is added to prevent the growth of bacteria in the water used in vials of flour. Household bleach contains aqueous chlorine. The concentration of chlorine in vials. The following experiment method was used to determine the concentration of chlorine in the vials at different times. From the vase of water. Suggest 2 reasons why the concentration of chlorine in the vase decreases with time. Well, this is not really a associated with the titration calculations here, but the thing about this is that chlorine is given off with time as a gas and so decreases. I'm not going to look too much at this experiment because these are actually rate experiments, so I'm going to leave that one. Feel free to have a look at them. We will do rates of reaction in due course. Again, the rest of question 2 here is electrode potentials, and we'll do those tomorrow night in our live webinar, looking at Ecell values, so on and so forth. The rest then of question 3. The following figure shows a graph of data obtained. So now we're looking at an acid-base reaction. The pH of the reaction mixture was measured initially and after each addition of sodium thiosulfate reaction solution. So here we got a pH curve that we've seen before, and what we're observing here is the initial change. We've then got our plateau, and here's our end point in the titration. Suggests a suitable piece of apparatus that could be used to measure out the sodium hydroxide solution. So when you're doing a titration, you're going to use a burette. The reason for that is because you can add varying volumes in the burette. Okay, a pipette only gives you 1 accurate volume. Use the information from the curve in the figure to explain why the endpoint of this reaction could be difficult to judge accurately using an indicator, and that's because the pH is showing a gradual change, and therefore the best way of doing this is to use a pH indicator that either changes over various pHs or to use a pH meter. But the reason is that we've not got a sharp endpoint. Here we then got an acid-base calculation. We're not looking at acid-base calculations in today's session, but if you have any questions about how to do those, please have a go at them and then do ask me at a later stage. Okay, so now an actual practical question about how to ensure that a pH meter is being measured accurately. And so the key here is that you have to calibrate a pH meter with known solutions. Okay, in other words, you've got to check that actually your pH meter is giving you a realistic value. So that's how we ensure they work. Other sources of error in a burette, well, you've got I think we looked at this last week. You've also got an air volume below the tap. Or the other one is that you might have the funnel stuck in the top of the burette. Okay, during the titration, the inside of the conical flask is rinsed with distilled water. Suggests why rinsing improves the accuracy of the titer. It ensures all reactants mix. In other words, anything that splashes on the side means that the reactants are going to mix with other things. And why does the extra water not change the volume of EDTA required? And that's because you're not changing the number of moles of EDTA. You're simply adding water. Okay. We've just dropped my live chat there. Okay, question 6 then. Let's have a look. So pH meters, well, why should you check them for accuracy before taking measurements? Well, the reason here is that they tend to change with time. So the pH reading changes with time, so they don't give accurate readings. So in other words, you have to go back and you have to recheck them. Okay, describe how you would obtain the pH curve for the titration. Essentially, we've seen that last week. If you're not too sure, do check out the answers. There's 5 marks going through this. I'm not going to write them all out because I'm sort of running short on time here. The simple thing is you're going to measure the pH of the acid, add alkali in known small portions, sort of 1 to 2 centimeters cubed at a time, stir the mixture, measure the pH after each addition, repeat until alkali is in excess, and add in smaller increments near the end point. So just check the answers later on if you want to check how to do this. But it's quite a simple, straightforward process. Make sure you're aware of it. Okay, then the next thing is, can you draw a pH graph? In other words, can you take some data? Key thing whenever you're drawing your data is ensure that your data covers a full range on your graph. Make sure you use a ruler, not like me just there, and ensure that it covers the large part of the graph. In other words, don't make it a tiny little sort of pH meter up like that. Make sure that it covers the full plot of the graph so that you can get the greatest measurement and therefore the minimum error from your graph. Okay, pH of neutralization we've talked about in our webinars before. Feel free to ask me questions about those later on. Again, we'll have a look here. So we're talking about here errors. We're now talking about percentage uncertainty rather than percentage errors. And just remember, the percentage uncertainty is equal to the error divided by the measurement here times by 100. In other words, for the pipette, assuming the pipette was a 25 centimeter cube pipette, it would be 0.05 times by 25, sorry, divided by 25 times by 100. You would whack that into a calculator and you would get about 0.2%. Okay, there we go. So estimating the pH. The rest of these aren't really practical related questions. They're more about the theory. Here we got some identifying some pH curves. I'm not going to go through this, but we can just see this is going to be a weak acid here with a strong base. This one here is a strong base, sorry, a strong acid with a strong base. This one here is going to be a strong acid with a weak base, and we got here a strong base with a strong acid. And we've got to think about appropriate which ones to tick here to get the correct answer. Finally, a table of acid-base indicators. Select from the table an indicator that could be used in the titration that produces curve B and not in that of curve A. Let's have a look at this. So in B and not A, so we want one which changes pH value around sort of, changes color around sort of 4, something like that. So if we look at our table, probably the bromo cresol green would be an appropriate one to choose. Give the color change at the end point of the titration that produces curve D when cresol purple is used as an indicator. So D, we're looking for something cresol purple when it's an acid. So cresol purple when it's an acid, we'd expect this to be yellow. Okay, I'm going to call it a day there. Don't forget to check out the site. All of the questions that were in the page can be downloaded from the quick question site here. Just jump in. There you go. They'll be there for the next day or so. There's the questions. If you want to get all of the answers, they're available from the past webinar section. If you're a member, just go along to the past webinars section of the site and you'll find today's webinar here is the 3rd of May and the answers can be picked off just there. Thanks a lot for listening. I really look forward to seeing those guys and girls tomorrow night for the webinar on electrode potentials.